Hello, welcome students. So we're continuing with chapter 13, talking more about NMR spectroscopy. We're focusing on proton NMR in this video. And you've already learned about chemical shifts. You can glean a lot of really useful information about a structure based on where the proton chemical shift is and the carbon chemical shift as well. I want to make sure you guys go back and look at those tables. I gave you a general table, but go back in your book and look at, oh, where does the aldehyde H come up? You guys should be able to look at a spectrum and just get some good information to help you figure out what the structure is. Okay, we're going to talk a little bit more about other ways to interpret the NMR, specifically with different splitting patterns that we see, and then how certain protons are not equivalent, even though you may think that they look equivalent. Okay, so we're basically covering these areas highlighted in green: the proton counting, spin splitting, and then proton equivalence. And then our last video will cover more on the carbon-13 interpretation. So here we have a spectra. Just take a minute to study the spectra. You have this compound here with the tert-butyl group. It's an ester, and you have a OCH3 and O-methyl group attached. And what you should have noticed is you have two peaks. What we're introducing here is relative areas. So just like the GC that you guys have utilized or seen spectra of in the past, you can integrate the area under a curve. That gives the amounts for GC, it gives the mole ratio amounts. Here, the area under the curve, if you integrate this, can give you the relative amounts of hydrogens present. So the integration can also be shown as a line. So the length of this line, for example, would be 1. The length of this line would amount to 3. Relative amounts 1 to 3. Most people just look at the readout of relative area 1 to 3. What that tells you is this could represent 1 hydrogen, and this can represent 3, or possibly 3 to 9. So that's how you guys are going to utilize the integration. It's going to help you figure out the relative amounts of protons of that type within a molecule. The other thing you should have noticed is this peak here, the pink one, comes out at around maybe 3.65. Here it's reading. That right there should have indicated this hydrogen that is represented by this peak is attached to a carbon next to an electronegative group. So here it's attached to an oxygen. Something down here is the aliphatic region, or saturated, C. So basically you have a CH3 attached to another C. Nothing attached close to a double bond or anything like that. So that's the kind of information just at first glance you should be able to glean from just looking at the spectrum. We're going to use what we just learned to analyze, not really analyze, but predict the type of spectra we should get from this compound, paraxylene. So this is a benzene ring with 2 methyl groups attached, one at the 1 position, one at the 4 position. When you have 1,4 substitution, we call that para, or just p-xylene. So I want you to look at the structure. Notice the symmetry of the structure. Identify how many non-equivalent H's there are present. So do you have the methyl groups? Are these 2 distinct methyl groups, or are they in the same type of environment? And then you have the aromatic ring H's. The next thing is, what ratio of peak areas would you expect if the spectra was integrated? And integration will give you those relative area amounts. So just take a moment to figure that out. So first of all, you would expect only 2 peaks, 2 absorptions, because there is symmetry within this molecule. Basically, each of these ring H's, the aromatic H's, they're identical because they all are in the same type of environment. They're all in a space where they are observing the same sort of connectivity and different types of atoms around them. The other thing is the methyl groups, because of the symmetry, those are also in the same environment. So those methyl groups are identical to each other, but different than the aromatic ring ones. So there are only two types of hydrogens in this. So you should only see two absorptions. The ring protons, the 4 different ring protons will absorb at the same chemical shift of 7.05. And then the 6 methyl H's will absorb and show a peak at around 2.23. The peak ratio, methyl to the ring protons, should be 6 to 4, which reduces down to 3 to 2. So the spectrum should look somewhat like this. We have a reference trimethylsilane at 0. A little past 2 are the methyl protons because they're attached to an aromatic. So they're not around 1.1 or 1.2 like the tert-butyl was. And then the ring protons will come up closer to 7. And here it comes up 7.05. And this should actually be a little to the left based on the scale. So the reason they are so much further up, they are attached to this aromatic ring with the pi bonding there. Okay. Let's talk about splitting patterns. So far you've only seen singlet, which are single lines as a peak, but sometimes we observe splitting patterns for our peaks. The reason is they're split by neighboring hydrogens. So if we look at bromoethane as a CH2 and a CH3, focusing on the CH2 protons, we would expect a peak between 3 and 4, which we do, but we don't see a singlet. The reason why is it's split by the neighboring 3 H's, and you see 4 peaks instead. You'll see the number of peaks that's 1 more than the number of neighboring H's. So if you have 3 neighbors, you'll see 3 plus 1 or 4 peaks. We call this a quartet. If we focus then on the methyl group, it has 2 neighbors, the CH2 group, so it'll be around between the 1 and 2 range. So here it shows up at around 1.68, and it'll be split by 2 guys, so we'll observe 2 plus 1 or 3 peaks. We call this a triplet. So these are just blown up of what you see here. Okay. So the other thing that we can observe is the integration. Here we see 1 to 1.5, which also can be represented as 2 to 3. So the 2 methylene units, which is the CH2 groups, to 3 methyl groups. So just start noticing certain patterns. This is an ethyl group. A methyl will be further upfield, and you will see it as a triplet because it's split by an ethyl group here. The 2 H's, sorry, not the ethyl group, but the 2 H's on the ethyl group to give you a quartet here. Okay, so we call this spin-spin splitting, and it's caused by coupling of the neighboring spins. Let me just tell you the origin of this. I don't need you to reproduce this, but I do want you to understand it. If I look at a molecule like this, and I'm focusing on HA. I'm talking about HA, and HA has a neighbor, HB. So the origin of these splittings is because HB itself has a magnetic field, and it can make a field for this nuclei here, the HA that we're talking about, making it bigger or smaller. So what that means is there is a spin of HB that can be aligned with the applied magnetic field when we do the NMR spectroscopy, or it can be aligned against it. If I am normally just HA a singlet with a signal here, if the spin is aligned with the magnetic field, it'll de-shield A and give the peak a little further downfield. If the spin is opposed to it, it'll give a peak of further upfield. So instead of a single line, this neighbor, because it contributes this magnetic field, it'll shift it so that you get one peak split in half and you get 2 peaks total. So since it's only split by one guy, you'll observe 2 peaks, which we call a doublet. Okay, so now let's apply this to the bromoethane. These are just words that I just described the field spin aligning with the magnetic field or applied field, the spin not aligning or going against it. Let me just show that visually. I'm going to talk about bromoethane. I'm going to first talk about the H2, CH2 group that's split by the neighbor 3 methyl H's. Those 3 H's can have spins aligned with the applied magnetic field or aligned against it. That's here and here. Or you can have some aligned, some not aligned, all these different permutations. So in the end, you split into 4 because you were split by 3 guys. You end up splitting to show 4 peaks, but the center peaks will be a little bit greater because there's more possibility for that sort of arrangement. So you observe what's called a quartet. And you do have the specific 1 to 3 to 3 to 1 kind of integration, or basically height. So now let's look at the methyl group. The methyl group is next to a CH2, so it will be split by the 2 H's on the CH2 group. Those 2 spins can be aligned with or against, or something in between, and you get what's called a triplet, 3 guys, in a 1 to 2 to 1 magnitude difference. The spacing here, which can be calculated in hertz, between those split peaks will be the same number. In this case, it's 7. If those guys were coupled together and cause each other to split. So we call that a coupling constant. It's given a J value, that's the coupling constant, and it should be 7 for each of those because they were coupled together. Okay, that's useful, especially if you're not sure if certain H's are next to each other. You can actually analyze the proton NMR spectra, notice, oh, these 2 peaks have identical coupling constants, they must be next to each other. So just to recap, there's the N+1 rule. Protons that exhibit N+1 peaks in the NMR spectrum possess N number of equivalent neighboring protons, and the coupling constant is the distance between peaks in a multiplet. So look at this. This is an isopropyl group. This is a classic key trademark signature of an isopropyl group. You have these identical or equivalent methyls being split by 1 CH, that proton. So that means these methyl groups, which will be in the 1 to 2 range for chemical shift, will be a doublet because it's only split by 1 guy. But that 1 H is split by these 6 H's. So you'll see this multiplet, a septet. So 7 peaks, these little spinning, little side guys as well. So just start recognizing these sort of patterns because that'll help you more easily look at a spectrum, identify, oh, there's probably an isopropyl, and you can confirm it by just further analysis of the spectrum. Okay, so I showed you the origin of some of those multiplets, which we can call any of these, the doublets, triplets, quartets also, in these specific ratios. So when you see that, identify that. For example, a quartet, 1 to 3 to 3 to 1, that sort of 4 peaks, that should signify to you, oh, there are 3 identical hydrogens nearby. Sometimes you'll get a spectrum that kind of looks like a quartet, but it won't have that exact ratio. So maybe it's just actually 2 doublets very close to each other. So just some summary of some rules. First of all, chemically equivalent protons do not show spin-spin splitting, meaning those identical methyls don't, H's off those identical methyls or equivalent methyl groups, they don't split each other. But if you have a neighboring guy, you'll get a multiplet with n+1 peaks, where n is the number of equivalent neighboring protons, and those will have the same coupling constant. Here, two groups of protons coupled together have that same J value. Okay, let's take a look at this guy. First of all, we have this formula here, and you're asked to propose a structure. You can do this. This is a spectrum. Notice the splitting pattern. Look at the molecular formula. The first thing I would do is, one, notice, first of all, the different types of H's in here. Here in your formula, you have a number of H's, but you only have 2 peaks. So what does that say to you? There must be some symmetry in the molecule. The other thing you want to figure out next is, what are the degrees of freedom? Meaning, do you have a double bond? Do you have a ring? And normally with 0 degrees of freedom, you have CN, H, 2N plus 2. So CN, N is 4, 2N plus 2 would be 2 times 8 plus 2 is 10. So that matches. You don't have any degrees of freedom. You do have an oxygen and their symmetry. So right here, what I want to do, and you guys can pause and try to figure out the structure too, is, but I want to make this symmetric. One thing you could do is put the O in the center. Notice the chemical shift, what that means to you here. Notice this pattern when you normally see this sort of pattern. Pause and try to come up with the structure. Okay, so first of all, I already mentioned there are no degrees of freedom, meaning no multiple bonds or rings. So it's just a straight chain something. Again, there are only 2 signals, 2 types of hydrogens in the ratio 1.5 to 1, or 3 to 2, or 6 to 4, because you do need to get to 10 H's. And so 4 protons are of one type and 6 are of the other. There's symmetry in the molecule to only get 2 different types. So the most logical explanation is further analyzing the structure, seeing that you have a chemical shift at 1.2, so that's saturated protons. You have the shift at 3.5, which must be next to the O, the electronegative atom. You have a triplet, so you have 2 neighboring protons for one guy, and a quartet, so 3 neighboring of another. So that right there to me is screaming ethyl group. And the compound, hopefully you came up with this, is diethyl ether. Here I show the generic regions where you're expecting the shift. So in this CO range here, you know, you have a CO that's in kind of centered around 3.5. The saturated H's, especially the primary guys, are closer to 1. So again, look through your book. Don't just look at this chart here, but there's one a little bit more detailed for the different types. So please look there for that table. Okay, what we need to talk about last is proton equivalence, and this is really powerful to help us just look at an NMR spectrum, which is more sensitive than carbon NMR, and just look at the different types of non-equivalent hydrogen. This gives us a lot more information about the molecule. So equivalent H's have the same signal, but non-equivalent ones are different. We've already experienced this, but there are degrees of non-equivalence that we'll go through. Sometimes it's hard to tell. Sometimes you're going to look at a structure and think, oh, those look identical. They look like identical environments. But even chirality plays a role. So we're going to go through and sort through which ones are non-equivalent. One trick that we're going to use is take a structure And we're going to replace hydrogens just kind of theoretically with some H group, like a X group, sorry, halogen group, like a chlorine, and see, oh, does that change the molecule? Does that change that actual structure? I'm going to sort through this with you and go through a couple different possibilities or different scenarios for you. So first of all, if the protons are unrelated and non-equivalent, we've been dealing with this, methyl versus the CH2 next door. Then if you were unsure, what you could do is replace either of these with an X and see if they just create a different isomer. So if I took these methyl groups and I want to make sure that they're different from these groups, if I replace one of the methyl H's with X, I get, for example, say it's a chlorine, we get 1-chlorobutane. But if I replace one of these methylene groups, these CH2s, with an X or chlorine, I get 2-chlorobutane. These are two different constitutional isomers. These are non-equivalent. The H's are in different environments. So they will have different proton NMR absorptions. Okay, second scenario, the two methyl groups. So we saw this with the parabenzene, the paraxylene, where we had the two methyl groups in the 1 and 4 position off the benzene ring. These are identical. I can look at these and see the symmetry in the molecule and look at these. But basically, you could do the test. If you think these are all equivalent, would replacing any of these H's with an X yield the same molecule? Replacing any of these would still give me, for example, 1-chlorobutane. So only one substitution product is possible. That means they were equivalent. They are, and they get a special name. They're homotopic. Those 6 H's are homotopic, homo for same, and they have the same NMR absorption. Okay. What if, however, they are homotopic but not identical? So let's look at a case where you look at H's on the same carbon. If I replace either of these, they can, with an X, they can yield a chiral center. So these are what's called enantiotopic, but there is no other chiral center in the molecule, so they will still have the same NMR absorption. Okay, the two possible substitution products are enantiomers. However, if there is a chiral center in the molecule already, like in this one with the OH forward, and I replace each of these H's, they are in different environments because they experience a different environment relative to this OH forward. So if I replace either of these with an X or a Cl, these create a new chiral center. They create possible diastereomers, so we call them diastereotopic, and they actually do have different NMR absorptions. So that's the killer one. That can sometimes be hard to see. Basically, my tip for you is if you already have a chiral center in a molecule, then you do have H's in different environments because they're diastereotopic. So then expect different NMR absorptions. Let's just end this video with practice on this proton equivalence. This is S-malate, shown here, and it's involved in carbohydrate metabolism. How many absorptions will you expect in the proton NMR spectrum? Meaning how many peaks, meaning how many different or non-equivalent H's do you see? So these are all carbons. This is a carboxylate here, a double bond O and an O minus. I know that because it's 8-malate on each side. And this carbon has an OH off of it. The red is O and an H, and it's forward. So right there, there's a chiral center. That means these two H's are diastereotopic because they're in different environments. They feel a different environment relative to that OH, this chiral center here with the OH forward. Okay, so then now you tell me how many absorptions Again, if you want to look at this just in a structural format here, these two are diastereotopic, and then you have this H, CH, and the OH. These are all going to be non-equivalent. So 4, you will see 4 different absorptions or 4 different peaks in the NMR. So just again, only when you have that chiral center will you expect that diastereotopic different peaks for carbon, H's on a carbon that you would have maybe initially thought, oh, these are equivalent. Okay, that's where I'm going to end here today. The next video and the last for chapter 13 will cover more on the C13 NMR spectroscopy.